Okay, I'd like to welcome everybody to the April 4th meeting of the IMAG MSM Working Group on Multiscale Modeling in Viral Pandemics at GLIMPRINT. It's our first April mini seminar. I guess we're lucky it's not April 1st for the seminar. As always, I need to remind you that this meeting is live streamed and recorded for future viewing. So please remember that. As always, Tom Helikar and myself are available to take your comments and questions. We have Jim Sluka and Lorenzo as the other members of the team. Please tell us what works, what doesn't work, how we can improve things, anything that you think can make this more effective as a community building exercise. We have our usual communication channels. They work better if we use them. We have the GLIMPRINT website. We have a Slack channel, which really doesn't get used that much anymore. We have a Twitter feed, MSM Viral. We have the IMAG MSM Wiki page, which is really the main place we put things, I think, still. There's a LinkedIn page for the group. And there's, of course, the YouTube archive, which has now, I think, 135 individual recordings, which cover something like 170 talks. So please help us make use of that material. The GLIMPRINT site could use your help developing it. We had that kickoff meeting a few weeks ago. We've had subcommittees meeting to discuss how to move forward with GLIMPRINT. Please help us out and build the community. Again, we have that Twitter handle, MSM Viral. If you're willing to use it to label your things, that would help us out. I want to make a few announcements. People will be aware that there are a bunch of funding opportunities. I think this group has contributed a lot to the creation of some of these opportunities. Reinhardt in particular, of course, gave that big address to NSF about the importance of these topics some time ago, and I think people who look at the RFAs will recognize text that was generated by this community in some of the RFAs. There is NSF Foundations for Digital Twins as Catalyzers in Biomedical Technological Innovation. It's due June 20th. Maybe people, I think a lot of us probably will be competing on that one. There is they're planning to make 6 to 10 awards. So it's going to be quite interesting to see what they go after. There's also Mathematical Foundations of Digital Twins, which would be of interest to many people here. Essentially the same due date, it's 1 day earlier, also making 6 to 10 awards. Some very interesting opportunities there. There also is the RFA AI 23007, NIH Centers of Excellence for Biosystems Modeling, Infection and Immunity across biological scales. So U54, people will recognize that. Again, that's something that this community has worked with NIH a lot on. I know many people in the room are going after that. I hope that somebody from our community many people from our community probably will participate going forward in those opportunities. There are a bunch of upcoming events near and far that may be of relevance to this community. Next week is Harmony 2024, April 8th through 11th. The physical meeting is in London. However, it is online. If you're interested in model sharing and community building, you can still register. It's free and participate virtually. There are going to be everything from demonstrations of Simun and VCell to discussions of model standards, SBAL, Copasi extensions, annotating SBML models. For my own particular interest, we're going to be having 2 panels on multi-cell modeling, standardization and sharing under the OpenVT logo. And so we'd love to have your participation in that. You can find the schedules at combine.org events. If you search Harmony 2024, you'll find all of that online. Again, that's something that you can do relatively last minute if you want to participate as a discussion. We are going to be organizing also a multi-cell modeling virtual community meeting on the 17th of April, focusing on defining reference models that could be used cross-platform to do platform validation. So if you're somebody who uses Physicell, CompuCell, Morpheus, or any of these other packages and would like to help us come up with a set of reference models that can be deployed across packages, we would love to have your participation. If you can't find the link easily, come to email me and we'll send that to you. There also is going to be an open VT workshop just before the SMB annual meeting in Seoul. If I know who's going to be at SMB, I can do a better job defining what that workshop should be. So please let me know if you're going to be at SMB this summer, and if you'd be interested in participating in a multi-cell standards and sharing meeting before that. The European side, as you know, the Europeans have been working a lot on digital twins. Lisbeth Garris and her colleagues coming out of VPH have this very large-scale initiative, EDITH. There is going to be an in-person Amsterdam meeting on July 15th, EDITH CSA ecosystem meeting. And that really, if you're interested in what's going on in Europe in the digital twin area, I strongly recommend thinking about participating in that. It's also, people remember from about a year ago that EDITH has been building this very large-scale roadmap on the technical challenges and issues for digital twins, medical digital twins. That had been closed, but that has been reopened for comments and extension. And so if you want to be a participant in the development of that roadmap, which is going to be guiding EU policy, I encourage you to reach out either to the general info at edith-csa.edu or directly to Lisbeth Garris and ask for access. I think she really would like to have more collaboration with the US on building an international standards framework for medical digital twins. And so I saw her last week in Luxembourg, and we talked a lot about this. They're very eager to build a transatlantic connection on this. There's also going to be the VPH meeting in Stuttgart, Germany. This is actually wrong. I have July 15th. It's actually that's a cut and paste error. I apologize. The meeting is the 4th to the 6th of September. They've reopened the abstract submission. They already have something like 350 submissions. All of the things that we do in this community would be welcome there. And so if you are interested in participating there, they do need abstracts pretty soon. But if you are interested, I would encourage you to contact the administration about submitting talks or demonstrations to that effort. It's also going to be followed up almost immediately thereafter, and I don't have this in the slide deck, with the Eurotalks meeting, which is going to have a heavy emphasis on novel alternative methods and modeling. So it's possible to go to the VPH meeting in Stuttgart and then the Danish Eurotalks meeting 2 days later, if people want to go to Europe for that. I'm also looking very much for suggestions for virtual meetings to discuss technical areas that we can work on under maybe this Open VT logo. Everything from code exchange and interoperability to descriptions of the domain applicability of models and modeling frameworks. Those are sort of ontological questions. But if you have ideas about things that you would like to see half-day or one-day or periodic workshops, hackathons on that would be related to multi-cell or multi-scale modeling and integration and sharing, please contact me and I'll do my best to help you give you the support you need to organize some workshops on these topics. As I say, these are some things that you might want to think about. We can come back to those. Maybe we should have actually, I could bring those up in a take a whole meeting for those. Okay. IU is still looking for faculty in computational bioengineering. University of Florida has been expanding under Reinhardt their efforts in computational biology in these areas. And so please contact the appropriate people if you're interested in those opportunities. The National Academy's digital twins papers are out. Foundational research gaps and future directions for digital twins. There are a variety of ways that's been published. Of course, many of the people in this community were panelists or contributors to that effort, both its origination and in its final form. So I think people will be pleased to see how the ideas from this community played out there. And something that I noticed the other day, which I wasn't aware of, is that in the latest 5-year plan in China, they've identified medical digital twins as one of the 6 core technologies that China wants to develop, along with things like electric vehicles and quantum computing. So medical digital twins are going to be one of the great focus areas in Chinese research and development. I think that may spur Europe especially into making larger scale efforts in the digital twin area. It'll be very interesting to see how that develops. We don't get typically very many Chinese colleagues on this call, which is a pity, because I'd love to get a take from some of our Chinese colleagues on how that will play out. It's a great opportunity for some of us to talk about. If you have a publication to share, please send it to Jim Sluka. We'll make sure that it gets put up on the IMAG page and also on the new GLIMPRINT page. We have published as a community a lot over the past 3 years. Help us keep that up to date. Make sure that you get the notice you deserve. We will have a steering committee meeting after some weeks of hiatus. We will have a steering committee meeting tomorrow at 11 a.m. Please join us. If you think you should be invited and you weren't, let us know, and we will do our best to get you invited. We're going to be focusing on the GLIMPRINT organization and also on this seminar series tomorrow. Please do help us out in this community effort. Are there any other announcements before we go on to our presentation for today? You can put them in.
I just put a link to that National Science Foundation book that James referred to in the chat.
Great, thank you. Thank you, John. That's great. Mitchell points out that there actually are some additional interesting multi-scale modeling conferences in Europe just after that VPH meeting. So you might be able to do a triple threat between VPH 2024, Eurotox 2024, and some other meetings as well, if you want to spend some time in Europe in September. Anything else that we should bring up before we go to the talk? Okay, coming up next time, we have Jim Sluka talking about predicting disease with broken models, which is actually sounds like it might follow on very well to today's talk. How do you use partial models to do prediction? Randy Hyland is going to be talking about some new innovative things that have been going on in the Physicell world. The Europeans in particular are using Physicell in conjunction with disease maps a lot in very effective multi-scale models. And so it'll be interesting to get an update from them. Going forward, as always, we need your suggestions. You've heard me say it before. If you've spoken before, that's fine. Suggest yourself again as a speaker. Suggest your graduate students, your postdocs, the people who've written papers that you would like to hear, people you'd like to collaborate with. We really depend on you to suggest our speaker list. Obviously, we want to bring people in who are going to be interesting to the community. And so we depend on your ideas for that. There's a tiny URL you can use to suggest speakers, or email me or Jim Sluka or Tom Helikar, and we'll make sure that we get the people you want on the roster. Okay, so now we move on to Rebecca Morrison, who's going to be talking about highly reduced models of random ODEs, a framework and analysis. And so as people know, I don't do elaborate introductions. I've already taken enough of your time with the preambles today because there were a lot of announcements. And I will turn the floor over to Rebecca.
Okay, here we are. We'll start with a little story to get us going, and then kind of review now what I see as sort of the basic framework for calibration, validation, and prediction using these models of highly reduced ordinary differential equations. I'll show you some examples from different fields. And then I'll end with a little bit of recent work that I'm pretty excited about right now. There's actually some analysis to get a sense of why these highly reduced models should even work in the first place. And this is mostly joint work with Riley Bandy, who's a PhD student here at CU Boulder. She's about to graduate in a month, and then she'll take a postdoc position at Sandia. Also, Americo Cunha, who is at Rio de Janeiro State University, and Estelle Baser from the American Institute of Mathematics, which just recently moved to Caltech. Okay, so this was back in 2018, right before I started my job at Boulder. I'd just given a talk on calibration and validation of these systems of coupled random ODEs. So this is a typical plot that I would work with. I have some variable, x1, and I have some detailed system. The information I have in that detailed system is given to me through data. There are these red triangles here. I have the reduced model that I'll talk about how we get that, but maybe some sort of naive reduced model that would be this green output here. And then I go through this enrichment process, calibration and validation of an enrichment that I'll talk about a lot today, and try to sort of correct for this gap between my detailed model and reduced model. And in many cases, even if my detailed model and reduced model are quite different, and I just kind of add a small correction back in, I can get a pretty good match with the data with this enriched model. And so here's this enriched model with mean and some quantiles. And I'll note here, this is actually for a prediction scenario, so that this enriched model hasn't been calibrated to this data. This is a new initial condition it hasn't seen yet. And it's doing a pretty good job. Okay, so I gave this talk, and Americo was in the audience, and he came up to me after and he said, look, I've got this really similar problem and maybe we can work together. And so the problem that he was working on was the Zika outbreak in Brazil from 2016. And so what they had in that case was a reduced model in orange here. So this is showing cumulative number of cases over the year. And the data, in these blue triangles is data actually coming from the Brazilian Ministry of Health. And so Americo and some collaborators took this kind of standard SEIR-SEI model that many people use to model Zika, and they did a really thorough search in the literature to really try to find the best parameters they could get. But really did this carefully. And with this SEIR-SEI model and these best parameters from the literature, they got this really terrible fit, this highly under-predicting what the data showed. And there's evidence that the data itself was really quite under-predicted also. Anyway, so this is what he had. And then this was also work he had done with other collaborators, is they said, well, let's try to calibrate this and do a better job. They had two different versions of a calibration, and they had some constraints on what the calibration could look like. So, maybe they could have gotten a slightly better fit calibrating the parameters, but it meant that, the the lifetime of a mosquito was something like 100 years. That gave a better fit to the data, but they didn't allow for that. They had a pretty constrained calibration problem here. And so you can see now it's doing much better, but there's still this kind of significant mismatch. And this was kind of where he was at with this problem. And he said, you know, maybe your this kind of enrichment idea for these reduced models could help. So we worked on it, and that's the main idea of this talk right now, is that what we have is a set of coupled ordinary differential equations. I'll call that system dx of t dt, and that's given by some initial reduced model that is a function of the state variables. And now I'm just going to add this pretty simple enrichment operator that depends on the state and maybe depends on the derivatives of the state. Okay, now the really important thing about this operator is that we're not adding it. This is not an like a discrepancy model on the model output. It's actually a discrepancy model on the model equations. So it changes the model equations, but because it lives within the set of differential equations, you can get this thing to respect whatever constraints you may have. You calibrate it to data. And because, again, it's not on the output, but it lives within the model, hopefully you can export it to other scenarios to actually make predictions. And we know that it's, in some sense, very sparse. You're not going to recover all of the missing dynamics. You're not going to scale back up somehow to the detailed model by adding this thing back in. You're still going to live at sort of the mathematical and computational complexity of the reduced model. Okay, so we added this thing back in, we calibrated it, and we got indeed a much better fit to the data. This showed up in this reference in chaos, and then there's some code attached to it now that's also been released if you want to play around with it. That does more than just this, but it has general UQ calibration and other things for epidemiology. Okay, we also then could do different things like make a prediction under the assumption that this data really was, say, 50% underreported. There were some reports that some people thought actually Zika was up to like 90% underreported. Only 10% of the cases were actually getting reported. But anyway, we looked at a couple different scenarios like that, and we were still able to adjust to those different scenarios. Okay, so then this is just one example. Maybe you may think, well, was this just lucky? But now I've looked at a bunch of different applications over the years, and in a bunch of different scenarios and a bunch of different applications, there's sort of the similar, they're all coupled ordinary differential equations, and we've seen successful enrichments in these very different fields. So now I've looked at Lotka-Volterra models and mathematical biology or ecology. So in this case, your detailed model could have tens or hundreds of species, but a typical model will only include the species of interest. So if you think back to your undergrad Diff-EQ class, maybe you were tracking rabbits and foxes. The first project I worked on was actually in combustion and chemical kinetics. So again, a detailed model may have 500 reactions, elementary reactions of chemical species interacting with each other over this lifetime of one chemical reaction, and something like 50 chemical species. That would be a good estimate for, say, methane combustion. But a reduced model, no modeler wants to actually use these high fidelity models when they're oftentimes these are just giving you source terms that then have to go into some much larger PDE, and you can't afford that really high fidelity model. And so chemists will use something like 10 reactions or 5 reactions or a global reaction and maybe 5 chemical species, maybe 10. Okay, then we just talked about the SEIR model. The most recent example I've looked at with Riley are these spring mass dampers. So in this case, people who work in computational mechanics and will simulate, say, the motion of a very complex object, like a vehicle on driving, the vertical displacement of a vehicle driving along the freeway, or say of a bridge, with a single spring mass damper. So these models are in practice very, very highly reduced from the real system, and yet somehow, with maybe a little bit of help, they do a surprisingly good job. Okay. So what's our common model structure? This doesn't quite capture all of the examples I just talked about, but it's sort of a good enough one that captures a lot of them. And it does include our epidemiology and our Lotka-Volterra. And anyway, is a good starting place. Okay, so this common model structure I want to think about is where one differential equation has a linear term in that variable. So dxi dt has this linear term in xi, and then it has a bunch of quadratic terms that are quadratic between xi and all of the other variables. So this is the common Lotka-Volterra setup. Here it's written a little bit more compactly, and then in vector notation we can write it like this, where diag of x is just a diagonal matrix with the x with the species along the diagonal. Okay, so that's our common model structure. And so a typical detailed model, if we think about the interaction matrix, and we now are simulating these with random matrices, we might have something like this, where this is over, say, big N variables. Here in this example, N is 20. And so we might have, 20 squared interactions that are actually happening. And for the detailed model, I'll try to use hats, A hat and B hat, for this detailed model. And then for a reduced model, maybe we'll choose M variables that we actually care about, and now reduce down just by taking that little submatrix of our detailed model. So now we're reducing down to 4 variables, and this is how we would build our reduced model. So it's a fairly naive reduced model, but if you have reason to believe that, if this is the interaction between your rabbits and your foxes, and you believe that, then you're going to ignore these, then maybe you're just going to keep that the same when you go and model your with your reduced model. Okay. So there's a lot missing when you do reductions like that. And what we've found is that these simple enrichment operators work surprisingly well to recover these missing dynamics. So what does this operator look like? I'm going to, again, add it on to my differential equation. It might look something like this. Was in the combustion case, we used something that was just linear in all the other chemical species. The one case I want to focus on today is we're going to add 2 terms, one that's linear in the state, and the second that's linear in the derivative. And that's it. Each of these get a parameter. So delta will be attached to the state, gamma attached to the derivative. And now this is this little piece of the ith piece of this operator that modifies my ith differential equation. And now I just need to calibrate delta and gamma. Okay. So here's a very high level one slide about calibration. Typically we use hierarchical Bayes. So we want to calibrate, say, 2 parameters, delta and gamma, for our M species of interest, maybe, or some variations like that, but you can think about that case. The data, we'll assume we have time series data from the high fidelity model or from the experiment, like a spring mass damper experiment, or from the world, like in the case of Zika. And now we have to set some priors. I'll set a prior, a parametric prior for each parameter. P is just standing in for, say, normal or log normal or some other whatever prior you want. And I'll assume that I have some hyperparameters that define this distribution. Okay, so here's where the hierarchical part comes in. I don't actually want to calibrate delta and gamma directly. I'm going to calibrate the parameters of their distributions. usually with MCMC, but you know, you could do something else too. And to generate our likelihood, we'll typically assume we have just Gaussian additive measurement error. Okay, how do we do validation? We use something that's called the highest posterior density sets. And our validation metric corresponds to the shaded area in this picture. So we have our enriched model. It depends on some parameters. Those parameters we assume are actually governed by distributions. We're going to calibrate the hyperparameters of those distributions. Once we have posterior distributions for those parameters, then we can propagate those through our model. That gives us our posterior. So let's say our model output for one point in time for one variable looks like this blue curve. What we're going to do is we're going to take our model output, we're going to compare it to our observation. This is model output now. This posterior, it's like a posterior predictive density that takes into account the fact that we also have measurement error. So I don't need to worry about that when I look at my observation. Now I look at my observation, I see where it crosses, and I'm really concerned with all of this area under this curve whose probability density is lower than what the observation itself has. So you can imagine if my observation falls in the middle of my output, then that shaded region is going to be very big. That's going to give me a large validation metric, a value. And I'm going to say in that case, I consider my observation and my model to be consistent with each other. If this value is very small, if my observation lies out in the tail, that shaded area is going to be very small, then my this validation value is now very small, and that indicates some inconsistency between my model and my data. So this is our sort of standard go-to validation that we use. It's kind of this pointwise validation, but you know, there's a whole world of validation, and that's a tricky subject. But anyway, this is what we've been using. And for any given pair of data and enriched model, we can compute sort of an average validation of these values, taking into account all of the data that we have. Okay. Okay, so to summarize all of this, I would say this is sort of our basic framework. Every problem you might deviate from this a little bit based on the specifics of the problem. But basically, step one is to identify the detailed system, even if you don't know exactly what it is. But we always keep that in mind, either as a high fidelity model, like in the combustion case that we know what it is, but it's too expensive, or an experimental scenario, or I'll say like data in the wild, where you, like in the Zika case, you really are sort of detached from a mathematical model. Somehow subselect a reduced model based on the species or say the epidemiological compartments of interest. I typically assume that these two things are given to me by the application or domain experts. Okay, there's of course lots of interest in just how to directly pick the best reduced model, but this is how I'm going to think about it for now. Then, given that reduced model, we'll propose an enrichment operator under whatever constraints we have. In the combustion case, you have very strong constraints. You have conservation of atoms, conservation of energy, things like that, if you have a closed system. The Zika case, you know, it's, well, cases can't be negative. That's about what you know. Then we'll propose this operator. Again, you know, in that doing so, we introduce some new parameters and their corresponding hyperparameters. Then we calibrate them with whatever data we can get our hands on. We validate, ideally for an entirely different scenario, like a different scenario in space or in time or with different initial conditions. And then we predict whatever we really want to know. Okay, so here are some examples. I'm going to go through these pretty quickly, and I don't think anyway, if you want to come back and talk about details at the end will do that, but don't worry about keeping track of every little equation. I just want to give you a feel of how this can actually work in these really different fields. So here are some Locke-Volterra type plots or models where the detailed system has 10 variables, the reduced one has 4. We introduce our 2 parameters per equation or per variable. And so in this case, you have this big reduction. You're omitting, a quadratic number of terms, 90 parameters in that interaction matrix and growth rate vector also, and you're introducing 8. And so here are 2 of those species, X1 and X3. You can see that when you calibrate your enriched model in blue, here to data, you do a pretty good job. But again, here are 2 validation scenarios where now this enriched model is doing a pretty good job, even though it hasn't seen this scenario before. Okay, again, this joint work with my student, Riley Bandy. Here's a nice prediction scenario from the hydrogen combustion. So in this case, the reduction is only from 8 to 7, but the right-hand side of the differential equations is much, much, much simpler because you're dropping out a lot of reactions. Here we have this type of linear enrichment. So all of the calibration here is happening with data from this 0D ordinary differential equation. Once we have that calibrated chemical reaction, we actually propagated it through into a 1D flame speed prediction problem. So this was like a really nice true prediction problem. And you can see this enrichment model is able to track the detailed model fairly well. Here's the Zika again. I've already basically seen this slide, but one thing I wanted to point out is in this case, so there's, you have your SEIR for your humans and your SEI for your mosquito. We don't really know what the true number of subpopulations is in this case. There is evidence that, and you probably all know more about this than I do, that, livestock could be involved, or non-human primates could play a role, or other species. And of course, this is all, spatially invariant too. That's a whole nother issue. But there are all these other populations that are being left out. Okay, and then this spring mass damper system, here we're going from 2 springs to 1, but you have position and velocity, so you're going from 4 to 2 equations. This is kind of a more complex enrichment in the sense where we take this reduced model on just 1 spring, we add in this sort of pseudo mass here, this X hat, and we're gonna model it just with a sinusoidal damped curve. And in this 4 to 2 case, you get this really amazing match between the enriched model and the data. It doesn't always look that good, but this is the nicest. Okay, so those are some examples. And to wrap up, I want to now get into the analysis. So yeah, during my PhD, I worked on combustion, then I worked on Zika, then I worked on these kind of mathematical ecology, then more recently springs. And in all of these cases, I would say it really bugged me why these reductions and enrichments could sort of even work in the first place. Like why should you be able to drop, 15 variables and 100 or 200 interaction terms or all of these things and still get fairly good, predictive models? And so this work was really born of trying to get at that question. And the problem is when you just have a numerical solution to some ODEs, it's really hard to say anything about how one model compares to another because you're just comparing. That's why I've looked at these plots, until my eyes glaze over, because you're just looking at these, that's what all you have, this numerical solution. So anyway, so here we go. So I want to just think about the the simplest case for this analysis when have a reduction from 2 variables, 2 differential equations down to 1. That's it. So my detailed model looks like this. My linear terms, my quadratic terms, I have x1 and x2. My reduced model, all I'm going to do, I drop everything that has an x2. So I keep x1 dot, I have my linear term here, and I have this a11 x1 squared. That's it. My enriched model, I come over here, I add my term that's proportional to the state, and my term that's proportional to derivative, and that's it. Now I just have to calibrate those. And okay, maybe you can get, yeah, here we call the reduced model partial. This is a term I noticed James used earlier too. Anyway, here, okay, we get a pretty nice match. So what's really happening? So we can rewrite this enriched model, move terms around. We have an x dot on one side and an x dot on the other. We combine those. And we have things that are proportional to the state, B1 and delta 1, and we'll combine those two. And so it's fairly easy to see that this delta 1 here, this delta term, can fix our equilibrium. So our new equilibrium from this enriched model is given by this thing. And so if we have data, A11 and B1 we assume are fixed, we have data for what this thing is at equilibrium, then we can just essentially, I mean, you can just set it. You don't even really have to calibrate too hard. Set this delta term to fix your equilibrium, and gamma 1, this term here, just doesn't interfere at all. So in general, we see in this new equilibrium is given by this modification here. Okay, so delta is fixing equilibrium. That we've known that for a long time. That's really easy to see. What about gamma? Okay, so now I've got this 1 over 1 minus gamma. Let me call that gamma 1 star. And now what I'm doing, well, I'm just kind of changing the overall rate of this equation. And you can think about, you know, multiplying this gamma 1 through all of these things. And in effect, we've just calibrated a new reduced model. Okay, where we have, instead of our reduced A and B, we have, let's say, A tilde and B tilde, where A tilde is this submatrix that we started with, A m by m. But then again, we have to, we're essentially scaling the rows of this matrix. And this B tilde, we modify by delta, and then again, scale. Okay. So that's fine. I mean, here, this is helpful to see in the sense that you could say, well, why not just calibrate your reduced model if that's all you're doing in the first place with this enrichment? We are, but at least we're doing it in a slightly smarter way so that, again, this is still a, you know, at least an M, the things that show up in your interaction matrix here of A, that's still a quadratic number of terms. We don't want to have to calibrate all of those. So we've still kind of reduced in some principled way the number of things we have to calibrate. Okay, so that's good. And now this most recent work, now we have a theorem. And this is the last bit. Okay, so I'll call this analysis via spectral power series. But we have to make some assumptions. Okay, we suppose this matrix A from our detailed system is invertible. C is A inverse B. That's the equilibrium of the detailed system. Excuse me. Now I want lambda to be the vector of eigenvalues of this matrix here, diag C times A. Those are the eigenvalues of the linearized system around equilibrium. And even though they're coming from the linearized system around equilibrium, they're actually sort of determining the behavior of the solution away from equilibrium. It's just what we found. So these eigenvalues are really important. We're also assume that these eigenvalues are real and negative, and that there are no vector integer solutions to this equation here, which just means that they can't sort of overlap as rational numbers. Like you can't have one be a quarter and another be a half, or minus a quarter and minus a half. Okay. Then there exists some T naught. It could be T equals 0. There exists some T naught such that our system, our basic system here, has a solution, x of t, that we write as this series, as this infinite series. So we'll have a coefficient. N is a vector of non-negative integers. And we just take the sum over all of these possibilities with these exponential terms. And you see that our eigenvalues lambda are showing up here. So this thing we proved converges not just as time is going to infinity, but for all time past some T naught. And again, T naught, that might be T equals 0. It might not be. It might be a little bit later. Or you might have to go kind of close to equilibrium. But it's not, in general, only holding at equilibrium. It's holding after some T naught. We can sometimes estimate that, what that T naught is. Okay, so this solution, so now we have a sense of what the behavior of the solution actually is, even away from equilibrium. And if you look at these terms here, we assumed our eigenvalues are negative. So if we have something that's really big in magnitude and negative, then this term is going to drop out very quickly, the contribution. Anything that involves that eigenvalue is going to go to 0 very quickly. Okay, so what does this mean for an enriched model? This is just rewriting this first part of the slide, the statement of the theorem again. Here's what our solution looks like. So it means that the largest m, lambda I, will dominate the solution. The ones that are closest to 0, those ones that are very, very strongly negative, the contributions will die out very quickly. So what we've found is that what our enriched models are really doing, they're calibrating delta to match equilibrium, and they're calibrating gamma such that the eigenvalues of A tilde, and we have just enough degrees of freedom to do this because we have, this is an m by m matrix and we have m gamma values. It's calibrating gamma such that the eigenvalues of this A tilde, or really it should be, yeah, excuse me. Well, it should be the diag. That should include the eigenvalues of the new linearized system. But anyway, that you get that from this A tilde. Match the most important eigenvalues from the full system. Okay, so this was a big sort of, I don't know, relief for me to finally see something like this, because now we have some indication that, you know, I know this is under these assumptions of you know, that the system is going to equilibrium and that the detailed system follows this sort of linear quadratic framework, but still in this case now we have evidence that yeah, it's not unreasonable, even if you have 100 species, if you only have 5 sort of significant eigenvalues, you do just fine with a reduced model over 5 species. Okay, so here's just showing you some results, just that these solutions actually do converge away from equilibrium. So here's 4 different initial conditions for the same model. The solid is our numerical solution, and the dotted are these SPS solutions. So you can see in these 3, it's doing a very good job from time t equals 0. Here, you know, I'd say you need to get to about time t equals 2. That T naught should be about 2 before you really see convergence everywhere. So again, these enriched models are capturing the equilibrium, and they're capturing these first m eigenvalues. Okay, and just to note a little bit of ongoing work, I've been looking now at detailed systems with nonlinear forcing and damping and real spring mass damper experiments, again with Riley. I've just started looking at analytic solutions for more medical applications like tumor modeling and imaging. This joint work with David Fuentes at MD Anderson. This is a really exciting application because right now they have some imaging problems where the solution to the ODE is the thing that really, really slows them down. So I'm hoping maybe we can, if we can use these analytic solutions, then we can also get much, much faster, you know, solutions, because we don't have to solve and numerically solve an ODE anymore. Also, of course, want to extend this outside this Lotka-Volterra class of models. That's what the Stahl baser. And then finally, what I didn't talk about too much today, but you know, in all of this, especially in the calibration, there's so many tuning parameters, there's so many decisions that have to be made. And so something that I've started thinking about with Sriram Sankarana Rayanan and Gautam Kaki, who are both here at CU, is to somehow try to automate this reduction and calibration through, say, formal methods, which they're experts in, and things like probabilistic programming. So, okay, that's it. So thank you so much. And I guess we have a little bit of time for questions.
Great, lovely. Thank you so much. The floor is open. I have some questions, but I try not to ask mine until the audience has asked theirs. Anybody have any specific questions to get started?
So maybe I can ask one.
Mitch,
Yeah, so this was a fantastic talk, Rebecca. Thank you so much. I'm gonna sorry, I have to move Zoom to this monitor here. Okay, really fantastic work. I think the first question I had was about, you know, is this model discrepancy in like the Kennedy and O'Hagan sense? And I think you immediately came out and said, you know, this is an input space. It's sort of in model space, not in objective function space or output space. So one of the questions I had, you know, working in model discrepancy in the typical sense, you know, we deal with a lot of identifiability issues when it comes to discrepancy parameters. Is that, I saw you using sort of Bayesian hierarchical modeling. Is that how you bypass the identifiability issue, or do you still run into that?
Well, we sort of so far have made the problem easy on ourselves in that sense. Because yeah, but yeah, all very good questions. But yeah, just to confirm, yeah, this is very different. Other end of the spectrum from a Kennedy-O'Hagan approach where you have a discrepancy function on the output. I've come to appreciate that sometimes you need to do that because say you have a black box model, or say your model is 3 million lines of code and different, you know, in different languages pieced together, then you may have to do that. But we're working in this kind of with the luxury of you know, completely white box model. Yeah, in terms of identifiability issues. So right now we really restrict all of the calibration to just these enrichment parameters. So again, we don't, I mean, there's an argument to be made that maybe we need to, that we or one might need to do something different for some of these cases. But when I calibrate the enrichment parameters, I assume that everything else is fixed and that I know measurement uncertainty. So that reduces that, so we just assume it's known. If you don't, then obviously there's interplay, right, between our enrichment models and the reduced models. And so that if you try to do both at once, then you need to be careful, I would say. And then one other thing I wanted to say about that, I mean, when just introducing this like quite small number of parameters per differential equation, you know, like a 1 or 2 maybe, then we don't usually have an overfitting problem of, oh, you know, we're introducing this huge thing that's totally flexible and it's just gonna totally, you know, overfit or something like that. And then the other answer is that, you know, that's why validation is so important, because if you are messing something up with that calibration or having that interaction or identifiability issues, that's probably going to come out when you move to other scenarios. So that we really try to make sure we're testing on other scenarios. Now, again, you know, that's easier when you have synthetic data. That's hard in real world data. Yeah.
Thank you.
Can I ask a question?
Please.
Hi, my name is Yi Jiang, and I'm always interested in model reduction problems. In particular, for example, when we are doing this cancer immunotherapy, you have to worry about the tumor, you have to worry about the immune system. Both are complicated enough, and then you have to worry about all their interactions. So in your recipe of this enrichment operator, for LV type of model, it's easy that you just do the linear term and the first order derivative. As soon as you have more chemical reactions of the Michaelis-Menten sense or the any other nonlinear form, how would you have to change your enrichment operator? Do you have any guess how to go about doing it?
Yeah, so the enrichment is, I didn't spend a lot of time talking about it, and that's one of the hardest things to do is to decide or to formulate what that enrichment actually should look like. And it absolutely needs to be more complex for or describe a sort of a richer space if the dynamics that are missing are more complicated. So that is kind of, I know I didn't say much just now, but one example that we can go back and look at is what we did for this spring case. So for example, here, oscillating systems are really hard. Everything else I've worked on that I showed you today went to equilibrium and did not, maybe it had one little bump, but it had and the analysis so far also is for these systems where all the eigenvalues are real and negative. So I haven't done an analysis like that for oscillating systems. Once things start to oscillate, it's much, much, much harder. So this was exciting that Riley was even able to get a nice result for an oscillating system. But in this case, you know, we tried with just a state and a derivative enrichment like the other ones I presented today, and it fails. It's not good enough. And, you know, it's just not capturing it's not capturing this missing dynamics that's really much more complicated. So in this case, we said, well, what do we know about what's missing? We know that we're kind of reducing from more springs down to a smaller number of springs. Those things that are missing are probably also oscillating. And we built that into the enrichment. So here, and we know that overall the system was damped. So that was a lot of information that went into this enrichment. And we built it as this, you know, damped oscillating function and then calibrated that. So I think there's different perspectives on how to do this well. There's some initial work now that tries to take a totally data-driven approach. Say, let me just get as much data as I can, and maybe I throw a neural net at this enrichment and try to calibrate the neural net. I come more from a physics community that doesn't trust neural nets and wants to kind of know what the equations mean. And so, you know, we try to stay in this framework of let's propose something that we can understand what the enrichment is actually doing. So, but absolutely, if you get if you get to a more complicated system, you probably need a more complicated enrichment, and you almost certainly need to rely on expert knowledge.
Thank you. Brilliant talk.
Thank you.
Leah?
Also, from my side, a really interesting talk. I was just wondering, because I'm not sure I totally understood. I mean, one of the biggest advantages, I think, of ODE modeling is that the interpretability of both the parameters as well as the variables, especially in comparison to more novel machine learning approaches. And I was just wondering how that enrichment term changes the interpretability of that system. Thank you.
Right. No, that's a great question. So again, so a couple really high level things we can say about that. It of course depends on the system. But in general, because you're still working, saying if you look at the Zika case, because you're still working with things that you know what they are, you still can interpret these things. So one sort of interpretation that we used when thinking about the Zika case was that we realized, well, this actually looks a lot like what people do in control. Because in control, what do you have? If you have a PID controller, you have something that's proportional to the state, something that's proportional to the integral, which I don't have here, but I've thought about, and something that's proportional to the derivative. So we have two of those things, and we're sort of trying to correct, you know, back to what the real dynamics, but we're not doing it at every instance in time. We're just trying to do it once for the whole system. So you can have kind of a control interpretation of something like this, where you're trying to adjust what's happening, you know, based off of, you know, what it is, what's going on in that state variable and what's going on in terms of its derivative. With the, oops, yeah, sorry, I forgot to add a, that should have a sum over J right here. Oh, I was sure that I had included that, or maybe it's on the other page. Sorry, yeah, there should be a sum over J here. So in this case, this was kind of, we said in this hydrogen case, what's the easiest thing we could do? The easiest thing we could do is maybe to add a linear correction. And in that case, what you're doing is you're just allowing for hydrogen atoms to move from H2 to H, or you're allowing for an OH to break up into O and H, or you're just allowing for linear transitions. So it's not, this actually broke down at some point because chemical reactions don't happen with linear transitions. They happen with these interactions. And we actually ended up building in these sort of pseudo reactions that were a little bit closer to what actually happens in chemistry. But yeah, so I think that in general, that is an advantage of this approach, is that when you build it, you're building this enrichment in terms of the things you already have, or something that looks like it, you know, and so you're trying to, you try to maintain that interpretability.
Thank you.
Thanks. Yeah, good question. And then I saw another hand. Yeah.
I think Mitchell had another question, but I'm going to jump in. So somebody who's not in this field, the first thing I would take away from this was something that I guess maybe is so obvious, or maybe I'm wrong in understanding it, which is that when you're doing your initial model reduction, you want to pick your variables so that the leading eigenvalues of the matrix of your reduced model are as close as possible to the eigenvalues of the matrix that you started with in the macro model, right? So if I'm going to decide which variables to throw out, it should be the ones that change that eigenvalue, the leading eigenvalues as little as possible.
Right.
That's sort of saying you're doing PCA, but it's not obvious that people actually do things that way.
So so I haven't kind of done it in that direction where you say, okay, I know the detailed system has, say, 5 important eigenvalues. Now, how do I pick the species that most closely match, so that my resulting submatrix, that its eigenvalues most closely match those 5? I haven't kind of done it in that direction. I think you could. I think that would be really interesting to do.
Wouldn't that minimize the amount you have to do with your corrector?
That absolutely would minimize the amount you have to do with your enrichment. That would make your enrichment process the easiest. So that
you
would be
need
good.
to keep some variables because those are your observables. So those you have to have those.
Then
But with the remaining ones, if you're free to
Right.
pick, you'd want to pick the ones that preserve the eigenvalue spectrum as much as possible, I think.
Right.
At least in the linear case. I just want to make sure I wasn't crazy in thinking about it that way.
I think that's right. But yeah, there's the question of where do you have data?
Right.
And then there's also this kind of, in the chemical kinetics world, sometimes the species of interest is, say, NOx, that is a very, very, very low concentration, but you're really concerned with how much NOx you produce. And so in a case like that, I mean, I haven't done the analysis, but I would guess you might drop that one. It doesn't make too much impact, but you don't want to drop it, because even these like very small amounts in terms of a quantity of interest are extremely important.
Right.
So
it's all you care about. So
that's what you care about. Yeah.
Yeah.
So you have to keep it. So.
But
Yeah.
it may not be informative for calibrating the model.
Right.
So yeah. So okay, that's great. So then I have one more, and I know Rita and Mitch will have more questions, but I want to just make sure I'm understanding.
Mm.
And my second question would be, a lot that you're doing here, and then you talked with E a little bit about how you change these things, and you showed the example of the oscillator. A lot of the theory comes about because you're using all these linear or first quadratic form, the structures.
Mm-hmm.
But then the linear operator makes sense. Now, if I have some complex set of feedbacks and Hill functions, then I'm not going to have linear it's not going to be linear in structure. And so then you could ask the question, what do you do? And you said, well, use information about, essentially, we know something about the physics, so we know something about the structure. You could be more, I hate to say, neural networky about it, and say, well, we understand the first time derivative is telling us what all those hidden variables are doing to the change, and the only way we can see it is through the change. So that makes sense that you'd use the first time derivative, the x dot for the corrector. If there were nonlinearities, then the natural thing to do might be to say, well, use x dot and x double dot, the second time derivative, which gives you 2 times in the past and allows you to look at higher order correlations. Now, if you're doing finite time steps, that probably works. So it's sort of you're going towards what I think of as a generative model. Whereas in the real world, if you're using really time derivatives, then the higher the time derivative, the more sensitive you are to noise in your system.
Right.
And so it may depend then on whether you really have finite time, whether you really mean the time derivative, or whether a finite delta t is something you could use. And I'm not able to formulate that as a very well-defined question, but conceptually, if I'm trying to fit a nonlinear model, I might try to add higher order time derivatives or higher order time steps in the back, and use that information in a systematic way.
Right.
I would expect something like the example you give for the oscillator would fall out of that automatically.
Yes. So, okay. So a couple of things. So I have thought about pieces of what you just said, and I think it's absolutely right. And there is some theory that backs this up. So first of all, which is one thing I want to point out, though, is that, these systems are not, but this is not a linear system. So we're getting a lot from the linearized version of it, but the system itself is nonlinear. So just that's one piece. But anyway, let me
But you're restricting the nonlinearity to quadratic nonlinearity, right?
quadratic. That's
Yeah.
right. Yes, just to quadratic. And then the other thing is that you can, so if you, but now say you start with actually a truly linear system, then it's known that you can exchange variables for derivatives. So that also inspired this work, because you can start with a linear system on n variables. You can get it down to everything in terms of x1, but you're just gonna have x1 dot and x1 double dot and so on. You know, every time you eliminate a variable, you introduce a derivative, but you can do that reduction exactly. You can get down just everything in terms of x1, say, if you want, but then you can do it with derivatives, or you can do it with integrals. Then you end up with nested integrals. But you can do that reduction exactly. I actually have a backup slide about that. That exact reduction also motivated this work, because and I have a little bit about when you can actually do these exact reductions. And so, yes, in theory, absolutely, you could add more derivatives, or you could add integrals, or you could add these nested integrals. But in practice, that's a lot harder to do. And so far in practice, on the actual examples, I've stuck with this very simple approach. But if there was good reason to, actually try to use a second derivative for an application problem, we could do it. Yeah.
Okay. Thank you for having the slide and being willing to educate me about the basics there. That was really helpful. Thank you.
So it's exactly the same way as if you think of a spring, a classic mass spring damper, that's a second order differential equation, right? For that, you get the acceleration of your spring. But the first thing you learn in diff EQs is, or I don't know, the first thing, second thing is let's instead of using one second order differential equation, let's use position and velocity, and now we have two first order, which is easier to solve computationally. So in that case, you're going the other direction. You're saying, let me introduce a variable, but get down, instead of two derivatives, now I only need one derivative, and I know how to solve that. I was kind of thinking of it the other way. What if I kind of only have access to some restricted set of variables? I know I'm missing things. Maybe what I can do is, instead of worrying about the fact that I'm missing all of these other variables, I'll introduce more information about the variables I have.
Right. And that to me is the fascinating question, which is, if I have a real time series and so I don't know what the governing equations are, how can I infer the analytical structure of whatever generated that time series?
Mm-hmm.
And so clearly you have to have some compromise. You don't want to start with just saying, I don't know nothing about what generated the time series. I want to have some mechanistic model, which is what you have here. Right. And now you have some residual, which is the missing information.
Right.
And what you are trying to do then is generate the simplest model you can that predicts that missing information.
Right.
And so, to me, it's a very fundamental. I mean, in the digital twin world, we know that the data sets are going to be rather limited in terms of their dimensionality. Right. We're going to have time series for some things, and most of the things we care about will be hidden.
Right.
Secondly, the models we're going to build are going to be very incomplete. And so we really want to know, can we use the residuals in those models to build better models and to identify what the key missing information is? Even if we can't interpret it, we'd like to be able to interpret it. But to begin with, we want to be able to predict. Mm-hmm. And so to me, ironically, I was talking about this with Jim Sluka earlier about, we don't really know how to do this properly. I said there must be some good mathematical theory that you come and present it, which is wonderful. But to me, understanding these issues in a fundamental way is critical. We can't do any of the things we dream of doing unless this kind of approach works and unless we understand it. And so I really, I think it's an essential enabling technology for the things that all of the very applied things that we're dreaming of here in terms of predictivity.
Right. I mean, it was driving me crazy. I kept having kind of nice results about really reduced models, but nothing to really back it up. So I would love to have the same analysis for, you know, a broader class where we can say, yeah, you again, and in this whole other class of models, you can do these big reductions. And as long as you capture this bit of information, you know, you're going to be okay. But anyway, okay, we should get to read. Sorry.
Thank you for the nice talk, Rebecca. And my question will be a very naive one, I'm sure, because I'm not okay. So when you are doing this and you want to reduce things, maybe the best direction is not one of the species or the other, but a linear combination of them. How do you know, even if they are just a limited number of these directions, right? So you have to make the combination before with all the variables before, and then how do you deal with that?
So I typically, this is a great question, and another thing that I make easy on myself by avoiding that.
Okay.
But there's a whole field of, you know, reduced order methods, ROMs, where that's exactly the kind of reduction you're going to get. You're going to find just in a really like pure, say, mathematical or computational sense, you're going to get the best reduced model. But what you may end up with is you may end up with a linear combination of an infected human and a susceptible mosquito.
Yes.
So because I have worked on these applications where, you know, I was talking to combustion experts, I was talking to people who are working on these SEI models. I don't think they want to do that. So I haven't done that type of reduction. I just assume my reduction is gonna, I had a term for it I was using for a while, have like this species, call it species correspondence. I'm gonna always just assume that I'm still working with, you know, a recovered human is a recovered human is a recovered human. So, and they're not gonna mix that way. But you can, I think so that also gets back to the interpretability. I mean, it's just a lot easier as to then interface with someone who's working in medicine or someone who's working in combustion. If you can say, you know, this is still a hydrogen atom, or, you know, so, but you might not get the best reduced model in a computational sense. So if that's really what you care about is, you know, absolutely the best reduction to get the, you know, fastest model,
Okay.
You know, with lowest RMSE and you know, the best fit in other ways, that then you might want to do something like what you mentioned. But I haven't done that.
Okay. Thank you very much.
Yeah.
Okay, are there any last questions? We've had a great discussion. Any last questions for our speaker today? I think there are lots of questions people could ask.
Yeah. Oh, go ahead.
I was going to say there are a lot of questions I can imagine people want to ask, but maybe we'll have to have you come back and give us another talk.
Yeah, maybe in person sometime. That would be nice. Or if, you know, if anyone in the audience, if I run into you at a future meeting, or if you want to talk, you know, here's my email. Feel free to reach out and be happy to keep talking at another time.
Okay, I want to thank you so much. That was really a perfect introduction to these ideas, and I really appreciate you coming to talk to us today. Thanks so much, everyone.
Thank you.